I want to continue with the logarithmic differentiation, and let me write an example about it. If y equals to sine to the power of ln t, okay, and the t is larger than 0 and less than pi, okay, and what about y prime, also del y over del t, question mark. Okay, don't forget, if you had like these equation, okay, and the logarithmic equation, okay, you must take the ln functions of both of them, okay, and I mean that ln y equals to, okay, and the ln of sine t to the ln t, okay, and it equals to ln y equals ln t times ln of sine t, okay, and that's equal to, and take the derivatives of the both of them, okay, take derivatives of both of them, and what will I do? It's easy, okay, this is 1 over y, and the inside of the y there comes del y over del t because of the with respect to t, okay, so this part 1 over t times ln of sine t, okay, plus ln t times cosine t over sine t, which is derivative of ln of sine t, okay, and after that we know del y over del t equals to, okay, y times, okay, and the ln of sine t over t plus, okay, and the ln t times cotangent t, okay, and the del y over del t equals to y was sine t to the ln t, okay, times ln of sine t over t plus ln t times cotangent t. That's the solution of that example. And another characteristic logarithmic differentiation example, okay, maybe not logarithmic, but you can obtain, firstly let me write the question, okay, and if y equals to, okay, and x plus 1 times x plus 2 times x plus, oops, maybe 3, okay, over x plus 4, okay, and the question is y prime, what's the y prime? Okay, firstly, when you look at this example, okay, you can differentiate this polynomial question by the rule, by the derivative rule of derivatives. Okay, but I want you to take this derivative by using the logarithmic differentiation rule, which was the taking ln functions of both of them. Okay, because of we know that if you had some product of the polynomial, okay, you can write them additional in logarithmic functions. Okay, I mean that ln of y equals to ln of x plus 1, okay, plus ln of, these are absolute value sign, as you know, and the plus ln absolute x plus 3 plus, I'm sorry, this sign is minus because of here is division, okay, minus ln absolute x plus 4. Okay, and they take the derivatives, both of them, and you will obtain, okay, y prime over y, because of the ln y prime, that means 1 over y, and it y prime comes and the y prime over y, okay, it equals to 1 over x plus 1, okay, plus 1 over x plus 2, okay, plus 1 over x plus 3, okay, and the minus 1 over x plus 4, right? And the y prime equals to, okay, and the, what will it be? It will be x plus 1 times x plus 2 times x plus 3 over x plus 4 times, this is the, you know, y, okay, and the times 1 over x plus 1 plus 1 over x plus 2 plus 1 over x plus 3 minus 1 over x plus 4. Okay, after that maybe you can simplify this total equation, okay, and it's your homework maybe. Okay, and let me continue with another example. Okay, find del u over del x, okay, and the evolution bar x equals to 1, and if u equals to square root of x plus 1 times x squared plus 1 times x cubed plus 1. Okay, and take the natural logarithm of both of sides of the equation, okay, and you will obtain ln u equals to 1 over 2, okay, times ln of x plus 1, okay, maybe it can be written like that, plus ln of x squared plus 1, okay, and the plus ln of x cubed plus 1, right? And they take the derivative of each side of equation, and you will obtain again 1 over u times del u over del x, okay, and it equals to 1 over 2 times, okay, 1 over x plus 1 plus 2x over x squared plus 1 plus 3x squared over x cubed plus 1. Okay, and at x equals 1, okay, and we know that if at x equals 1, okay, from this equation, okay, u will be 1 times 2 times 2, and it will be, I'm sorry, 2 times 2 times 2, and it will be square root of 8, so it equals to 2 times square root of 2. Okay, and after that, what can we say about it? Del u over del x, okay, and the x equals to 1, okay, and the 1 over u goes to the other side of equation, okay, and it will be 2 times square root of 2 over 2, okay, and the 1 over 2 plus, okay, and the 2 over 2 plus, okay, 3 over 2, right? And after that, some simplification, okay, and you will obtain square root of 2, okay, and there will be 1 and 2 and 3, okay, so it's equal to 3 times square root of 2. Okay, and I will continue with the growth and decay, okay, which is the new subtopic, okay. But I will only interest, okay, the growth of exponential and logarithms, okay, and the other subtopics of this topic, which are exponential growth and decay models and interest on investments and logistic growth. I don't interest of them, so you can omit these 3 subtopics, okay. I only interest the growth of exponential and logarithms, okay. And let me continue with them. I mean that okay. And for this subtopic, okay, I use and also will use exponential functions to model the growth rates of quantities whose rate of growth is directly related to their size, okay. And let me give you some theorem and some property, okay, to understand this, okay. And maybe, okay, and if, okay, x is larger than 0, okay, then, okay, ln x is less than or equal to x minus 1, okay, and see at the page 196 for proof, okay? And the another theorem also, it can be written the growth properties of exponential and natural logarithm function, okay? If a is larger than 0, then first limit x equals to infinity x to the power of a over e to the power of x, okay, and it equals to 0. And the second property, okay, that means e to the x, okay, equals to infinity faster than the numerator part, okay. That means please understand and analyze this limit, okay. Limit x equals to infinity, okay, ln x over, okay, x to the power of a. This times it equals to 0 again, because x to the power of a equals to infinity faster than the numerator again, okay. And the third part, limit x equals to, minus infinity, okay, and the absolute x to the power of a times e to the power of x, and it equals to 0, okay. Because of this is faster again, okay, exponential function equals to infinity faster than the absolute value x to the power of a, okay. So the fourth property, okay, and the last one also, limit x equals to plus infinity, x equals to 0 from right hand side, okay, and the x to the power of a times ln x, okay. We approach to 0 from right hand side because natural logarithm functions is not defined on the left hand side of 0, we know that, okay, and from the domain of the natural logarithm functions, and so it's equal to 0, okay. And this property will help us, okay, some identity in future, okay, and they don't forget all of them, and you can also find all of these properties, okay, proof at 197 page, okay. So I will pass to the 3.7 subtopic, okay, which is the inverse of trigonometric functions. Okay, and the first one, the arc sine, which is also can be written inverse sine function, okay. And let us define a function, okay? Okay, sin x, okay, and to be a sin x function, okay, and it's the sin x function, but the sin x interval, okay, and that means its domain, okay, domain of sin x function, okay, and it's the restricted function, okay, because of it's a periodic function, okay, we know that. And I mean that the restricted function capital letters S sin x, okay, it's the function. Of course, its characteristic same as the sin x function, but its domain restricted, okay, from the minus infinity to plus infinity, okay, so its domain area this interval, okay. And what I mean, okay, let me sketch it, okay, on the coordinate system, okay, and I'm sorry, yeah, okay, and oops, maybe okay, and firstly let me assign this point is plus 1 and this is minus 1, okay, and this point is pi over 2, and also this is minus pi over 2, okay, and okay, and this dot lines function is y equals to sine of x, okay, and this blue line, blue curve, okay, and it's the restricted sine function, which is capital S sine x, okay, that is that. So okay, that means we will omit, okay, these parts, okay, and the left hand side of the minus pi over 2 and the right hand side of the pi over 2 part we will omit, okay, for this restricted function, okay, and now we'll interest the inverse sine function, inverse sine function or arcsine function, okay, and this will be, and what did we restrict this sine function, okay, because if you don't do that, okay, you will not obtain one-to-one function, okay, if you want to take any inverse function, okay, your function must be one-to-one, okay? So we restricted that sine function to get and to evaluate, okay, inverse sine function, okay? And now our blue line, blue curve is one-to-one function, okay? So we can take this inverse, okay? So the inverse sine function or we can write it the arc sine x, okay? If and only if, okay, x equals to sine y, okay, and the if and only if x equals to sine y and the restricted area, which is the minus pi over 2, okay, and the if and only if y is less than or equal to pi over 2, okay. And the graph of inverse sine function, let me sketch it, okay, and as an interesting sketching, okay. And now inverse sine function, okay, will twist on the y-axis, okay. We know that the sine x function twists, okay, on the x-axis, but now you will see the inverse sine function and it will twist on this part of the coordinate system, okay, and let me write the values, okay, this point's value, okay, and this is the 1 over 1 comma pi over 2, okay, and this point is the also symmetric minus 1 comma minus pi over 2, okay, and that's the x, that's the y, okay. So let me write these equations. Inverse sine of sine x or arc sine of sine x, okay, it equals to x, okay, for, okay, minus pi over 2 less than or equal to x is less than or equal to pi over 2, okay, and the capital of sine, I mean that restricted sine function, okay, we know that, and the inverse sine x, okay, that means sine of arc sine x, so it equals to x, but its interval is different because of we always interested in the inside of, okay, and so I forgot, okay, and let me correct it, okay, this part must be again capital, okay, and this part is capital, okay, inside of the equations domain is true, plus 1, okay. And now what can we say about this inverse sine function, okay, and let me continue. and we know that the for example, if we know that sine 0 equals to 0, okay, so we can say that the 0 equals to inverse sine 0, okay, and the sine pi over 3 equals to square root of 3 over 2, okay, and we know that the pi over 3 equals to arc sine square root of 3 over 2, okay. So the sine pi over 2 equals to 1, so 1 equals to inverse sine pi over 2, okay. And the inverse sine x means inverse, not reciprocal, okay. And the reciprocal of sine x, okay, let me write it. Okay, x means inverse, not reciprocal, okay. That's important. The reciprocal of sine x is this, okay. Reciprocal of sine x, okay. That's the different of from here, okay. This is inverse and that's the reciprocal, okay. So it will be of course 1 over sine x, and which is equal to, okay, cosecant x, and don't forget it, inverse sine x does not equal to reciprocal of sine x, okay.